Okay, now let us design FIR filter using windowing techniques. So first of all, let us assume a transfer function or an impulse response. Say h of n is our given impulse response. Which is obviously infinite in length. Fair enough. So what we shall be doing is using the windowing technique, we must derive h prime of n from h of n, where h prime of n will be having finite samples. So let us observe diagrammatically how the windowing technique works. Say we provide an input h of n to some sort of a window. So this is our window over here. This is our, so this is our window, and say this part is the screen. Just arbitrary nomenclature. And the output we will get is h prime of n. So what the windowing method essentially does is that it takes infinite number of samples from h of n and passes it through the window, where some of the samples get caught in the screen and is left back. So in layman's term, when we are passing this through the window, so through this small aperture, not all the samples of h of n will get through. Some very small number of samples of h of n will get through. We are calling it this to be h prime of n, and a larger number of samples will be discarded via this screen over here. This is the basic principle of our windowing technique. So mathematically, h prime of n will be equal to h of n times w of n, where w of n is known as the window function. Now suppose let us draw an h of n. So this being one sample, there is one sample over here. This will go up to infinity. Just arbitrary sample values, and this will go up to infinity. This is our h of n. This goes from 0 to n. So now our task is to limit using a window and take only 4 samples. So h of n has infinite number of samples. So in our case, h prime of n will have 4 samples. Since we have defined that the number of samples in h prime of n or the output impulse response should be 4 samples. Now we can take 4 samples in different ways. Say we can take any 4 samples, so 1, 2, 3, 4. We may take these 4 samples through the window. This is our window. Otherwise, we can also take 4 samples from here as well. So 1, 2, 3, 4. So this will be our window function w of n. This will be also another window function w of n. Similarly, we can shift the window and take any numbers of for any group of 4 samples. So now a condition arises. If we take the window for n less than 0, so if we take for n less than 0, such in this case we have taken a sample having the value n less than 0. So this type of window is known as the anti-causal window. And consequently, if we take window from 0, n equals 0 to n greater than 0, this will be, so n greater equal to 0, this will be our causal window. So this is anti-causal, this is causal. Now in linear phase, we have discussed that all the filters must be causal in nature. So anti-causal window is undesirable. Although we can design anti-causal window, what we need to do in order to make the window or the filter feasible is, after designing this anti-causal window, we can simply shift it by the required number samples to make it causal. And that way this will also work. So this is our window. So in general case or mathematically, the window does not seem like this aperture over here. It has a mathematical value. So say in our case, w of n is shown as under. So w of n looks something like this. Since there are 4 samples, it will have more samples, but the values will be 0. So this is w of n. So this value is 1. So say w of n is a rectangular signal or an rectangular impulse train, which is having the number of samples from 0 to 3. So what I mean to say is that the w of n window will also have infinite number of samples, but other than the required number of samples, all the other samples will have the value equal to 0. So now in order to get h prime of n, what we need to do is multiply h of n times w of n. So if w of n is multiplied with h of n, say from here and here, so say let us give this value. So this is 1, 2, 1, and sorry, this is 2, 3, 2, and say this is 1. So we are concerned with 4 samples. So 2 times 1 will become 2, 3 times 1 will become 3, 2 times 1 will become 2, 1 times 1 will become 1, and 0 times 1, 0 times this value will become 0, and it will continue to be 0 from this side and this side as well. So all we are left with is h prime of n to be something like this. So this is our required h prime of n. So this is how, from a very varying number of frequencies, we limit our number of frequencies to the desired value. This is the essential function of the windowing technique. Okay, now let us see what are the window functions or different types of window functions that are prominently used in the filtering designs. So, types of window functions. Now, generally speaking, there are numerous window functions, and this can be designed or customized as per the user requirement. But in the broad sense of calculation or ease of calculation, 5 types of windows are most prominent among filter designers. The number 1 window that we have shown earlier is the rectangular window, which is denoted by WR of n, and the function having a value 1 for 0 less than equal to n less than equal to m minus 1. This m is obviously provided by user, and it will be 0 otherwise. So what does the rectangular window looks like? We have shown earlier. So this is m minus 1, all of them having a value of 1. This is WR of n. Okay, so this is our rectangular window. The next window, which is known as the Hamming window, named after its inventor, Mr. Hamming. Hamming window WH of n will be 0.54, 0.46 cosine of twice pi n, m minus 1, 0 less than equal to n less than equal to m minus 1, and 0 otherwise. So Hamming window will follow this expression for n which goes from 0 to m minus 1, and it will be 0 otherwise, like that of the rectangular window. So our next window of concern is the Hanning window. Hanning, double N. Two completely different people, Hamming and Hanning. WHN of n, this is given by 0.5 minus 0.5 cosine of twice pi n over m minus 1, 0 less than equal to n less than equal to m minus 1, and 0 otherwise. So this is our Hanning window. almost quite similar to the Hamming window, just this coefficient or this constant values are changed and there is a negative sign. Sorry. The next window is our Blackman window. So Blackman window has the window function WB of n 0.42 plus 0.5 cosine of twice pi n over m minus 1, 0.08 cosine of 4 pi n over m minus 1 for 0 less than equal to n less than equals to m minus 1 and 0 otherwise. So this is our Blackman window. And the final window, which is the Bartlett window, which is having the function WBT of n is equal to 1 minus 2 mod n divided by m minus 1, where modulus of n goes from is less than m minus 1. So among our 5 different window functions, all the first four windows are causal window because the limit goes from 0 and forward until m minus 1 in all the cases. Only the Bartlett window is the anti-causal window, where the value of n goes both in the negative direction and the positive direction. So we can solve windowing problems using the Bartlett window, but we need to do a simple step of shifting the result to make the impulse response causal. So this is our theory behind the window, or rather the windowing technique. So let us look at a mathematical example. So the problem is stated: design an FIR filter where m is equal to 5 using the Hamming window for frequency response, that is the desired frequency response, hd of omega is equal to e to the power minus j twice omega, where omega goes from minus pi by 4 to pi by 4 and 0 for pi by 4 mod omega to pi. So this is our problem. We need to design the FIR filter using Hamming window. Now this is a simple example. In the examinations, the window functions may be different. It may be Hamming window, Blackman window, Bartlett window, rectangular window, and also the value of m may vary from 0 to any integer, and also other changes can be made to the desired transfer function over here. So that is for the examination part. So let us go into the solution. First of all, we need to plot the diagram. So if this is our plus omega, this is negative omega. This is hd of omega's modulus or magnitude. So the value is from minus pi by 4 to pi by 4. So the filter will be having values from this region to this region. This is minus pi by 4 to positive pi by 4. And it will be 0 in this direction and this direction. This can be derived from over here. So we can write omega as plus minus of omega. Modulus of omega can be written as such. And this can be further simplified to plus minus pi by 4 omega to plus minus pi. So minus pi by 4 to minus pi, the value will be 0. And from pi by 4 to positive pi, the value will also be 0. That is determined by this boundary condition. Here now, if this is 0, this is our low frequency part, and up to this is our high frequency part. So our desired effect is that we are going to design a low pass filter. So now applying DTFT, so applying DTFT, we can write h of n 1 over twice pi integral, which goes from minus pi to pi, h of omega e to the j omega n d omega. So now let us divide this region into 3 parts. So this is our first part. This entire portion is our second part, and this is our third part. So what we need to do is also divide this integral into our 3 subregions. So h of n will be equal to 1 over twice pi integration minus pi to minus pi by 4. H of omega to the j omega n d omega minus pi by 4 to positive pi by 4, that is for the region 2, h of omega e to the j omega n d omega, and finally for the third region, positive pi by 4 to positive pi, h of omega e to the power of j omega n d omega. Now from the diagram it is quite clear that the region 1 and region 3 will be 0. That is, the area under region 1 and region 3 will be 0. Hence it will render this integral to be equal to 0 and also this integral to be equal to 0. So simply all we are left with is h of n to be equal to one over twice pi minus pi by 4 to pi by 4 h of omega e to the j omega n d omega, plugging in the value of e to the h of omega from the given expression, we get 1 by twice pi b e to the minus j twice omega, the j omega n d omega, the limit goes from minus pi by 4 to pi by 4, and simply multiplying these two exponents we get e to the j n minus 2 omega d omega. There is 1 over twice pi over here, minus pi by 4 to pi by 4. Now solving for this integral, we get h of n 1 over twice pi e to the power j n minus 2 omega, when integrated with respect to omega, will rather remain same, e to the j n minus 2 omega, and this will be divided by the coefficient by which omega is multiplied, which is j n minus 2, where the limit goes from minus pi by 4 to pi by 4. Just basic integral calculation. So plugging in our limits, we get 1 over twice pi e to the power j n minus 2 pi by 4 minus e to the power minus j n minus 2 pi by 4 divided by j n minus 2. So now from the Euler's relation, we can simply write sine theta to be equal to e to the j theta minus e to the minus j theta over 2j. So we have 2j over here, and if we consider this entire expression to be theta, we can simply write it to be, so can be simply written as 1 over pi, bringing this n minus 2 sine n minus 2 times pi by 4. So this is our h of n. Now all we need to do is apply the window function. So let us use a fresh page for that. So applying window function, we get h prime of n to be equal to h of n times w of n. In our case, w of n, which is the Hanning window, is 0.5 minus 0.5 cosine of twice pi n over 4, n 0 to 4 and 0 otherwise. Since we have considered the value of m to be equal to 5, so n will limit from 0 to 4. Now we can write h prime of n to be equal to 1 over pi times n minus 2 sine n minus 2 times pi by 4. This is our h of n, and 0.5 minus 0.5 cosine of pi n over 2. Just simplifying this term, this will be our w of n. So now all we are left with is to determine the value of h prime of n for all values of n going from 0 to 4. But before doing that, let us verify one case. If we put n is equal to 2, so this value becomes 2 minus 2. So 1 over 2 minus 2, which is equal to 0. So 1 over 0 will render this term, entire term, to be undefined. So we need to determine h prime of 2 or h of 2 in some other manner. So h of 2 can be written as the inverse dt of t 1 over twice pi minus pi by 4 to pi by 4 h e to the power minus j 2 omega, which was our h of omega, times e to the power of j omega n. In our case n is 2, so this will be 2. So this is our value of h of 2. Just simply getting the value from this expression. This expression shown over here, where n is equal to 2. This value will come from our question over here, h of omega e to the j omega n, n will become 2. The rest will remain same. So finally what we get is, by simply multiplying these two exponent terms, is that 1 over twice pi minus pi by 4 to pi by 4 d omega equal to pi by 4 plus pi by 4 over twice pi is equal to 0.25. So this is our required value of h of 2. Now let us determine for n equals to 0, n equals to 1, n equals to 2, n equals to 3, and n equals to 4. This being our value of n, where we are to do is h of n multiplied by w of n, where h of n is 1 over pi times n minus 2 sine n minus 2 pi by 4, and 0.5 minus 0.5 cos of pi n by 2, our window function. And by the magic of calculator, we can simply determine h of 0 to be equal to 0, h prime of 1 to be equal to 0.113, h prime of 2 to be equal to 0.25, prime of 3 to be equal to 0.113. This value we have taken from over here, and h prime of 4 to be equal to 0. So once again, if we match, the first and last value will be same, the second and second to last value will be same, and there will be a median value in the middle, which is a check for our filter, FIR filter design. So with this, we come to the end of the problem of our FIR filter design using windowing function. In the next video, we shall be discussing about the various methods of designing IIR filters using various transformation techniques.